Hi. So far we know how to sample from a distribution, meaning let's say we have our low dimensional distribution Z. We know how to take this Z and create, our higher resolution X. So we're just able to, let's say, sample from this, P model of X. So we know how to sample when it's a simple sampling. Let's say we train our GAN on pictures of faces of a lot of people, and then we can sample from that distribution and create a new face. But what if we wanted to do more? Remember in that demo we saw there was like a slider for, let's say, age, right? So here it's like maybe 10 years old and here it's 90 years old. So how do you give that additional information along with that Z, right? How do you also give a condition? This condition is what we use to then control the output of a generative model such as a GAN, a generative adversarial network, and let's see how. So what we want to do is we want to control meaningful attributes of our output of our generative model. And we know that any model that maps a lower dimensional latent space, which is Z, to a higher dimensional output can be used for making conditional models, and this higher dimensional output is X. And our GAN happens to be such a model, such a generative model. So like we've discussed many times, this Z is lower dimensional as compared to the input image. And additional latent vectors, conditions, can then be added, which will then be mapped to distributions similar to our factors of variation in data. And this condition can be of many types, and we will see what people have done with this next. And based on that, we can then generate data conditioned on labels, conditioned on text, conditioned on other drawings, images, and anything that you can convert to this vector representation, right? So you'll take your condition, you'll also then convert it into, a condition vector, and then that will go in addition to our Z to the generator, right? So that is how we will train our model. And one of the first papers to do this was Isola et al. In 2016. They called it Pix to Pix. And what they did was, given an image such as this one, so this is the condition. The condition is the semantic segmentation where you have a label per pixel as input, and based on these labels, it's able to generate a realistic image. Similarly, given the condition of an image such as this one, which is, let's say, a satellite image, right? So it's a satellite image of, let's say, a neighborhood of a part of a town. We're able to generate these clean satellite looking images, right, with roads and so on. Similarly, given a sketch of an input bag, it is able to generate the output such as this one, and this is the ground truth. And what they do is something very simple. So how do you train the discriminator? Training the discriminator is straightforward, but the only difference here is that we now have tuples, right? Instead of just an image, we have an image and its corresponding sketch. So to the input to the generator along with Z, we give it this X. We expect it to give out an image which should look nice, which should look like this one. But how do we train it? How do we train the generator or the discriminator? We give it these pairs of, so when we train the discriminator, we can give it like real images. These are from the real images and their corresponding let's say edges. You can just run some canny edge detector, get this image, and whenever the discriminator sees a pair like this one, which is the dataset image and its corresponding canny images, it should output real. Similarly, when it takes in the output of the generator, but then you also club it with the input to the generator, and then you feed it into the discriminator, and it should output fake. So what are Isola and Isola doing? In their paper, Image to Image Translation with Conditional Adversarial Networks, CVPR 2017. CVPR is a major computer vision conference, and I try to attend it every year. For example, in 2026, it's happening in Denver. What we do is we transform image from one domain to the other, for example, from drawing to photograph, from maps to satellite imagery like we saw, or from semantic labels to a photo. like in the autonomous driving photo we saw. It requires paired data for training. For example, the drawing and the image of the same shoe, yeah, like this one. And the adversarial discriminator learns to discriminate between real and fake tuples which have the edge image and the original photo. And here in this figure, what do we see? We see the training of a conditional GAN to map edges to photo, right? So this edges is what I'm talking about, these edges. And the discriminator D learns to classify between fake, synthesized by the generator, and real edge photo tuples. The generator G learns to fool the discriminator. Unlike an unconditional GAN, both the generator and discriminator observe the input edge map, right? Usually the generator does not see any image in the case of, let's say, our unconditional GAN, but here in addition to the latent vector Z, it also gets to look at this image of the edges. Yeah, but remember, we need these paired images, right? Pairs of the shoe, the image of the shoe and the drawing of the same shoe, and so on. So this was one of the limitations, but this was one of the first papers to do this conditional GAN. Then came this, this seminal paper, in my opinion, called CycleGAN. This comes from Efros's group at Berkeley by Zhu et al., called Unpaired Image-to-Image Translation using Cycle-Consistent Adversarial Networks, ICCV 2017. ICCV is another major computer vision conference. And what they came up was something very interesting. What they do is, given an image, a video such as this one, it is able to generate a video of, say, the horse doing exactly the same thing. And this is really hard to kind of do it in a paired way, right? Because you'll never have data like this. And what they do is something very, very interesting. So what they say is, we're going to use two generator networks, G and F. Yeah, and let's say our X is zebra and our Y is horse. So X is zebra, Y is horse. What we are saying is, we're going to convert our X to Y, our zebra to horse. And similarly, we're also going to convert our horse to zebra. So initially, when we start, obviously our network is not trained, and when you put the condition, so now we have this whole image as a condition, and we try to get the output of the horse, it will probably not look like a horse, but we want it to eventually look like a horse. And like we always do, we will have a fake horse and a real horse, because we have a giant database of horses, we have a giant database of zebras. So when the generator outputs something that should look like a horse, we will again train the discriminator based on that real and fake, and based on that discriminator loss. So we often show this discriminator loss as dx and dy. So the discriminator loss here is saying that my generator G should produce images that look like a horse given this input X, right? So given an input of a zebra, I want the output to look like a horse. I have a discriminator loss on that. But this is the clever thing that they do. They say that now what I'm going to do is, I'm going to take the same image that you have produced, yes, and I'm going to give it to this other generator F, which is supposed to take images of horse and give me the zebra, and I'm going to compare the initial and the final position. Meaning, we start with our zebra, we go to a horse, y hat, we compute also the discriminator loss, but then we put the same thing here, and then we get this x dash, and we say that this x and x dash should be close to each other, right? So we also then minimize this cycle consistency loss. Similarly, when going from horse to zebra back to horse, we say that okay, from horse we go to zebra, we obviously have our discriminator loss for the zebra here, but then from the zebra we want to go back to the horse, and we want to say that these two Y's, these two horses should be close to each other. So you would penalize if they're not close to each other, right? Because you started from somewhere, you want the cycle consistency to happen. You start from a horse, you go to a zebra, but when we bring it back to the horse, I want them to be the same horse. So you can again minimize the loss here. And Additionally, it has this strict assumption that a pair of corresponding images x1 and x2 from two different domains can be mapped to a shared latent space z, and last few layers of the encoder or the first layers of the decoder have shared weights. And four different losses: E1 G1, reconstruction, E1 G2, E2 G1, the cycle consistency loss, and the adversarial loss using D1 and D2. And there is also this VAE loss on Z, and I'll talk to you about the VAE loss slightly later. But we essentially have these four losses. Yeah, so we have our discriminator loss, we have our E1 G1, which is the first cycle consistency, and then we have our E2 G1, E1 G2, and E2 G1 loss, right? So we have all these different losses, which then enable us to get results like these, because you cannot just have, how do you get horses and zebras to be the same number, be the same, age, be the same positions, poses, I don't think the same background. It's very difficult. And so they came up with this clever way of using cycle consistency to then, do this. Similarly, I'll not go into detail, but because this is older and we have better ways to do it, but this is one of the first papers which applied it to autonomous driving domain, where for the same image, they were able to create so this is an image of a scene during day, and they're able to create an image of the same scene during night time. So this is important to get the same scene at night time, because if you were simply driving and collecting data, you would not get the same scene, right? Because there'll be a different configuration of cars, different configuration of traffic lights, pedestrians, and so on. But what if you wanted to validate exactly apples to apples? Oh, for this scenario, what happens when I run it at night time? And for this, they're able to do this using, again, that cycle consistency, and you're more than welcome to check it out. This was a NeurIPS 2017 paper, image to image translation, and they called it UNIT. So they could then apply it frame by frame on video. There was no temporal consistency, but for example, an image here is during daytime, and you see it's the same configuration of cars. If you look closely, the same configuration of the traffic sign that you see here approaching, and so on. Similarly here, you want to evaluate like summertime versus wintertime, and if you look closely, you'll see it's exactly the same situation, just that the trees have turned barren, but it's the same configuration of cars, the same configuration of traffic lights, traffic signs, and so on. Now this was another seminal paper by Karas et al. In ICLR 2018, so ICLR, the International Conference for Learning Representation, started by Jan and Bengio. It was a seminal paper because this was for the first time we were able to do like really high resolution images as output. Prior to this, we were not able to generate very high resolution output because learning was hard. This paper is called Progressive Growing of GANs for Improved Quality, Stability and Variation. And the idea here is really simple. What they do is, of course, latent is your Z. So from your Z, they say in the first step, they only have a very small network which creates just a 4x4 image of the face, right? So this is just a 4x4 image. And then this image, so the generator creates this image, and this image goes into the discriminator D, and then you do your real and fake business. Now, what you do is, once you have trained this, once you're able to do these 4x4 images of the face, you then go a step higher, you double. So you use pre-trained this and pre-trained this, but then you slap one additional layer on top, these 8x8s. And then you say, okay, I want my output to be this 8x8 here, right? So now I have this 8x8 image as output. And you just train this one and this one. And then you keep doing this, right? From 8, then you go to 16, one by one. Because going from, the small resolution is okay because you already are able to create that 8x8. So now you're able to create 16x16. And you keep doing that until you come to say 1024x1024. But if you directly go to 1024, we were not able to, learn. We were not able to train such networks. And this was for the first time when we were able to generate beautiful images like these. So here I want to show you the training paradigm, what the training looks like. So the training has started, And here we are generating the 64 cross 64, now 128 cross 128. This is the amount of time you've spent on training, and this is the amount of data that the model has already seen. You see that by now in 12-13 hours it has already seen, let's say, 10 million images, and we are now at the full resolution. And you will see that they will also now interpolate between these images, meaning you have your Z1 and you have your Z2, and you can always interpolate between Z1 and Z2. You can say, something like lambda times Z1 plus 1 minus lambda times Z2, and you can then interpolate between these two latent vectors Z1 and Z2. And the whole idea is that when you interpolate between them, and lambda of course here is between 0 and 1, when you interpolate between them, all those intermediate states should look natural, and at the same time it should be like a smooth interpolation. So this is that interpolation test that they are doing here, right? So you see that not all intermediate states are very plausible, but most of them are, and mostly it looks like a smooth interpolation. So this is a qualitative way of checking how, if our generative adversarial networks are working well, if they're learning well. And then we'll also talk about the quantitative evaluation side of things. So this is qualitative, visual, but then how do you get a metric? How do you get a number? How do you evaluate such generative models? And that's a topic for the next video. Now, what the previous people did here, progressive GANs, they were able to generate it for faces. They were able to do single classes. For example, you could do, let's say, cars, you could do bicycles, but the output was not as good, and they still couldn't use one model with different class labels for all classes. And the Big GAN was the first such paper in 2018 in Europe, where they could do this large scale GAN training for high fidelity natural image synthesis, where they could generate class conditional samples generated by the model. So you have one same model, and you just give it the label dog, and it will be able to create, and of course your latent vector z, and if you give it different z's, it will give you different dogs. Similarly, natural images, butterflies and burgers. If you look closely, the butterfly will be defective a little bit, right? The wings seem broken, but this was the state of the art in 2018. And now here they are doing two things, right? So they're interpolating not just between the latent vector z1 and z2, so say 1 minus lambda times z2. They're also interpolating between the class labels themselves, right? So interpolating between two classes. So this is what we see earlier, but now here what they're saying is, okay, I will now interpolate between two classes. I will still have my z1, so it will be still my z1 and z1, but I will change my class, right? I'll change my class smoothly from lambda times c1 to 1 minus lambda times c2. Right, and class 1 happens to be some fish, maybe a shark. Class 2 happens to be a dog. Similarly, maybe this is a better example where our first is, let's say, so the class here is a bird, and the class here is maybe an insect, and look at how smoothly it interpolates, right? It is almost like a mixture of a bird and an insect. So again, the latent vector remains same, z1, z1, but then the class vector, here it's c1, and here it's c2, and in the middle we are simply interpolating c1 and c2. Okay, and this is what we see, the interpolation between those two classes. This is again video synthesis. So this is for the first time people were actually trying to do videos, and this is from NVIDIA and MIT. And what you could do was you could give it a video in one style, and it will create a video in another style. For example, we gave it edge images as input, and now it's able to give like a full colored video as output. This was again NeurIPS 2018. If you go further in this video, you will see that you can also do it. You can change, let's say, the vegetation just by giving it different inputs. But yeah, this was just basically GANs applied to input. Here, for example, you give it edges, and you can then generate faces. You can also generate these edges from a different face and then apply it to the third person. So this was the beginning of, let's say, generative modeling, which have now become commonplace. This was a seminal paper because GANs had kind of taken a backseat But scaling up GANs for text to image synthesis was a seminal paper again from Adobe Research, where they kind of created this big GAN, right? So they called it GigaGAN. So this GigaGAN could do very well at that time, but again, GANs have kind of taken the back seat. But GANs have been part of, let's say, the CVPR 2024. In CVPR 2025, we again saw a bunch of paper, also 26, there are some. But GANs, you may want to know about it. You may want to use the latent states of it. You may want to use pre-trained, let's say, things called as style GANs, which are very similar to conditional GANs that we've already discussed, to then maybe condition our diffusion model, to condition some generative model that we work with. So it is important to know, because it might still be very useful for providing a prior to these modern methods.